Just to recap the material covered in module 3.1, where we introduced the concept of Bravais lattice, which is a mathematical construction, and we said that in 3 dimension you can identify 14 unique Bravais lattices or unique arrangement of lattice points. So the questions now which now comes is, what is the relationship of these Bravais lattices with real crystal or the physical crystal? The physical crystals are not made of points, rather they are made of atoms. So this module would deal with the question of how to represent physical crystals using the concept of Bravais lattices. To answer that question, let me first show you how you can represent a periodic structure using the idea or the concept of lattice. So imagine you have such a periodic structure. It can be periodicity of anything, any object. You can deconstruct such a periodic object into these two things. So you have a set of points which repeats itself in space, and you have an object which is being repeated in space. So a periodic structure can be deconstructed into a set of points which I would call as a lattice, and a repeating motif, the object which is being repeated. So imagine if I place this repeating motif on each lattice points, I would get the periodic structure back. So that's how I would use the concept of lattice to introduce physical crystal. But before I go that, I want to introduce the concept of the mathematical concept of convolution. So the convolution of two functions g and h in one dimension is denoted as g star h, and what it basically does, this convolution operation, is that it maps this g of x function onto an h of x function, which is mathematically given via this expression. If f of x is the convolution of g of x and h of x, it is equivalent to an integral operation such that g is a function of x prime, such that x prime is the running index from minus infinity to plus infinity, and you integrate it with by multiplying it with h of x minus x prime for a certain value of x. You keep on changing x, and that's how you generate the convoluted function f of x. What does it mean graphically is shown here. So you have a g of x function, which is kind of a delta function, and h of function, which is some kind of shape, double-sided arrow shape like this one. And if you convolute these two functions, the convoluted function is something like this, where this arrow-like shape gets mapped on each of these delta-like functions. So if you look, there's another example here. You have a zinc-like function, and you convolute it with a series of delta peaks along x-axis. This is the convolution of these two functions, where the zinc gets repeated again on at the point where this delta function lies. So now we can go back to our problem and see where does this convolution leads us in terms of representation of periodic function. Just to complete it, you can have a convolution not only in one dimension but for functions which are in 3 dimensions, and the integral would look something like this. So coming back to this description of a periodic structure in terms of a lattice and a repeating motif. So this lattice which is points repeated in space can be represented by a function like this, which is a delta function in 2 dimension. So if you imagine that r is a position vector such that the origin is defined at one of the lattice points, then whenever small r is equal to the lattice vector capital R, you get a peak at the delta function in 2 dimension. So a lattice arrangement would be a sum of many such peaks in 2 dimension. And let's say, so this capital R is such a lattice vector. Similarly, let's say the repeating motif is represented by some arbitrary function b of r. Then the periodic structure, which can be then represented by c of r, is then simply a convolution between this lattice function L of r and b of r. So to conclude, the periodic structure is a convolution of lattice and repeating motif. This repeating motif is given a certain name and it's called as basis. So basis of a lattice or basis of a periodic structure is the repeating unit within a certain periodic structure. And it's a very powerful concept which we would use in the later slides. So what we learned in the previous 2 slides is that you can represent any periodic function, any periodic structure, if you can identify the repeating motif or basis and the lattice on which it is repeated itself. So now let's consider such a periodic structure. Can we describe this periodic structure in terms of lattice and basis? So the first thing you need to do is identify what pattern is being repeated, and can you impose a lattice on such a, imagine I put periodic dots over here. So these are something which I intentionally put in this structure. So would these lattice represent kind of a brevet like structure? For example, what if I look around this point, this lattice point, I see these 4 small circles or the dark gray circles. Is it the same with all these lattice points? So if I look here, I have exactly the same scenario, So I can, by putting these dots, I have kind of make a condition where things, the environment around those points are exactly the same. Now I can identify a unit cell using those extra small points I inserted into this periodic structure. This unit cell is something, if you can think about it, this unit cell is repeated uh, in that periodic structure again and again, and if you you can fill the whole space with such a unit cell and you would reproduce the whole periodic structure again. So keeping the points which I introduce myself and removing the rest of the details, I get something like this. And this you can easily identify is a brevet lattice pattern with a lattice spacing given by A. So I take a specific lattice point and take it as a reference, and and define a basis with respect to that lattice point which I label at 0, 0. And the basis consists of 5 structures, for dark gray circle and one light gray circle uh, positioned at specific location. So for example, uh, the small the large light gray circle is placed at position a half and a half. The four dark gray ones are located at quarter quarter, three quarter and a quarter, a quarter and three quarter of a with respect to this reference lattice point. So we can identify this unit cell as the primitive unit cell in the basis in the lattice we defined earlier, and we can also define our primitive lattice vectors as well by a1 and a2. And now what we can do is we can superimpose our bases on the lattice itself. So this unit cell would be replaced by this basis structure. And if we do it for all the lattice, we get is the periodic pattern which we get before, or which we started with. So we reconstructed the whole periodic structure using the lattice points we defined and the basis we defined earlier. The thing is, what happened is now you can identify the location of each of these small circles with respect to the lattice points, and that's the convenience you get by defining a lattice. For example, if I want to define the position of this light gray circle, then I need to identify the location of this lattice point with respect to my origin, and it's in general is given by n1 and n2, these two integers, plus a half and a half, because this light gray circle is a half along one lattice vector and a half along second lattice vector as identified in the bases which defined earlier. And similarly, you can identify the location of the rest of the four dark circles within this unit cell as well, and you can do the same for any other structure within this periodic structure itself. So the identification of lattice and bases help you to fully identify all the location, all the structures within any periodic pattern. Let us now consider another periodic structure, which is a honeycomb lattice. We have seen such a lattice before, but we concluded last time in the last module that even though this pattern is a periodic pattern, but it's still not a Bravais lattice. Now the question is, can we make such a lattice, a Bravais lattice, by some intelligent guess of lattice points? So imagine if I insert lattice points in this honeycomb lattice and see if the environment around the lattice points are exactly identical for all of them. So if I look at the small circle around this lattice point, I see a pattern, and if I match this pattern with the pattern around this lattice point, they are exactly the same and identical, and as is true for all the points which I have arbitrarily put inside this periodic structure, which means that these lattice points can be used to represent this periodic structure as a Bravais lattice by a suitable choice of a basis. So what I can do now is identify a unit cell within this lattice structure which I have superimposed over this honeycomb lattice. the unit cell would look something like this. So this pattern which is inside the unit cell, if it is replicated for all these different lattice points, would reproduce the honeycomb lattice back. So this slide shows only the lattice points and the rest of the honeycomb lattice has been removed. And as you can see that these points clearly represent a Bravais lattice with a unit cell given by this. Now you can define primitive unit vectors which would describe such a unit cell like these given by a1 and a2, and you can define a1 and a2 like this in the xy coordinate. So if a1 has a magnitude a, then a2 would have this much magnitude along x direction and this much magnitude along y direction, and this you can easily check by the geometry of a hexagonal shape. Now we can take this point as we have taken this point as a reference point of the unit cell, and we can define the basis with respect to this reference point as shown here. So that's the basis, and in the basis we have two circles, one a dark circle and one is a light gray circle, and this is our reference point, and we have to identify the position of these two objects within a basis using these two primitive lattice vectors which we have defined. Just to let you know that the difference in color of these circles is just for identification purpose. You can just simply have both of them in black color. It's just for. So as you can see that this dark gray circle is 1/3 away from the reference by along A1 and 1/3 along A2. So why these two um, lattice vectors, this is the relative position of this object within the basis with respect to the lattice point. And this other object, which is the light gray circle, is 2/3 along A1 and 2/3 along A2 away from this reference point. So we have identified the position of the basis objects with respect to one of the reference lattice points. Now you can superimpose this basis on your lattice point and you get back your hexagonal lattice. So what you can infer from all this exercise is that you can represent a hexagonal lattice as a Bravais lattice but consist of a two-point basis, which means that you can construct a basis made out of 2 points or two lattice points, and then that would get you a Bravais lattice out of a hexagonal lattice. Another way of looking at this honeycomb lattice is like this, that imagine you only consider these black lattice points, then you can make Bravais lattice out of them by such a unit cell. So now I have uh, taken this as my reference point and these are the unit cell, and I can replicate as many unit cell as I like and fill up the whole space, just ignoring the light gray circle. And then I can make another unit cell uh, entirely made of this light gray circle and make another lattice which would be a Bravais lattice. So what you can say is that the honeycomb lattice, which is originally a non-Bravais lattice, can be made out of two superimposing Bravais lattices. So here is a test problem for you. We are now in a position. This is a periodic define physical crystal. It seems so. A physical crystal, a Bravais lattice, is a convolution between a lattice and basis. You can define a primitive unit that the bases and unit vectors are made out of and also find out rather than how many atoms which we or how many points are there in the primitive unit cell. So this would result into a periodic structure where the atoms would be periodically repeated, and this is what a physical crystal is. So let's have a look at a few examples of physical crystals found in nature. To describe a physical crystal, you need two things: a Bravais lattice and the coordinates of atoms, molecules, or ions with respect to Bravais lattice points. So the first example we're gonna look at is sodium. A sodium crystal is a cubic, body-centered cubic system. So the lattice we know is BCC lattice, and the basis is sodium atom placed at 0, 0, 0, which would mean that you have to place the sodium atom at each lattice point within a BCC crystal, exactly at the lattice points in this case. So that's how a conventional unit cell of a BCC is. That's the top view with the atoms at the edges or at the corners, and the one in the center of the unit conventional unit cell at half the height from the bottom plane. So to describe a BCC unit cell, a conventional unit cell, you need 2 points because a conventional unit cell contains two lattice points, as we have seen before. So you have two lattice point. You need one lattice point 0, 0, 0, which is let's say this reference one, and then you need another lattice point at a half, and a half, which is the one at the center, and these two, the coordinate of these two fully describe this fully conventional unit cell. So the question is, what would be the coordinate of the resulting atoms? So since the bases consist of a 0, 0, 0, so with the two latest points which describe the conventional unit cell, you have to just add a 0, 0, 0 and a 0, 0, 0 with them, and what you get are the atomic position of sodium for this crystal, sodium crystal. So in this conventional unit cell, you have a sodium atom here and a sodium atom here in the center. What about the rest? What about this one, for example? So this would be the reference for the unit cell, for the conventional unit cell, which is just above this unit cell, which is shown here. So if you're gonna add a basis to that unit cell, then you would add um, one atom at this location and another atom at a sodium atom at one half there. So you would get the other conventional unit cell, and similarly for all the others. So you only need to describe two lattice point to describe a conventional cell of a BCC. The next example is a sodium chloride crystal, which consists of a cesium atom and chlorine atom. Uh, the lattice is cubic, primitive cubic, and the basis is cesium at 0, 0, 0 and a chlorine atom at a half, and a half. So cesium, which is a positive ion, and chlorine, which is a negative ion, is an ionic crystal. So normally the positive ions are depicted in smaller spheres and the negative ions are depicted in bigger spheres because of the extra electron they have. They get the overall size of the atom increases. This is the top. So what you have is a primitive unit cell. So you might be wondering why it's not a BCC, because it looks like a body-centered cubic system. The answer is not a BCC because you have a cubic system, but on a cubic system you have a basis which consists of two atoms and not one atom. So let's try to find the coordinate of the atoms in this unit cell. So the first thing you need to know is how many lattice points have to describe for a you need to describe for a primitive cubic cell, and the answer is just one. And which one that would be? Let's say any reference lattice point. For this case, it would be this one. So it is located at 0, 0, 0. That's the lattice point, and you can add a cesium atom at 0, 0, 0. So that's why you have an atom at this location. But that's not the whole basis. the basis has another atom which is chlorine atom as well. So that's why with 0, 0, 0 you have to add a basis atom of chlorine at a half and a half. So what you do is you start with this lattice point which is at 0, 0, 0, and you add another basis point to it, that of chlorine atom, at a distance a half and a half from this lattice point, and you would get your uh, the location of the chlorine atom. This whole conventional cell, so because for primitive cubic cell you need only one lattice point, so this lattice point, one full lattice point is 0, 0, 0, would describe this whole unit, conventional unit cell over here, and it consists of just one basis, not two bases, because one basis consists of two atoms. So that's a important distinction to note. That's why it's not a BCC or a body centered cubic system, but rather a primitive cubic system. Let's have a look at copper crystal. Copper is a metal with metallic bonding in such crystals, and as we have mentioned in one of the lecture notes, or in one of the lectures, that metallic bonding is, it doesn't have any direction, but the bonding becomes stronger when the atoms are as close to each other as possible, or in other words, the more dense the packing is, the better, the stronger a metal is. um, so most of these metals, they do have dense packing, and because of dense packing, we would see in one of the later module is that dense packing results into mainly two kind of crystalline structure. One is face-centered cubic, and another is hexagonal uh, lattice structure. So uh, in case of the copper, it is a face-centered cubic lattice, and the basis is copper atom at 0, 0, 0. This is the unit cell of a conventional unit cell of an FCC crystal, and there's a planar view from the top. No, this basis of 0, 0, 0 would mean that we take a FCC lattice or an FCC unit cell and place a copper atom at each of the lattice points. To describe a conventional FCC unit cell, we need to describe four lattice points. So the first lattice point I would take is one of the reference point, which is at 0, 0, 0, and we add a copper basis atom to it at 0, 0, 0 location, exactly at the reference point. So you have a copper atom at position 0, 0, 0. Then the next lattice point is on one of the faces, which is 1/2, 1/2, 0, which is this face, and we put an atom, uh, copper atom, exactly at that location, because the basis is say 0, 0, 0, which means it put the atom exactly at the lattice point. And similarly for the other faces as well. So you have uh, uh, three more atoms, three more lattice points, one at this face, one at this face, and one on the face which is here. So you need to describe four lattice positions to describe the full copper lattice. Uh, and this copper unit cell would consist of four bases, and each base is that of a single copper atom. So let's have a look at a couple of very important crystal structures. Um, these are diamond crystal structure and zinc blende crystal structure. Starting with diamond, it it is like an FCC crystal with atoms that of carbon. However, there's a slight modification with respect to an FCC crystal. is that the unit cell contains four extra atoms at four corners. For example, you can identify one, you can see that there's an atom over here, an extra atom here, another one here, another one near to this corner, and the other one near to this corner. And these extra atoms of carbon in this FCC of carbon are located at a distance of quarter, quarter, and a quarter uh, away from the reference points or away from the lattice points. So uh, this is in this case, this structure is that of a diamond. All the atoms are that of carbon. Uh, Similar structure is formed also by silicon, which is another very important material for silicon technology and IC circuits. A parallel structure is that of a zinc blende structure, in which these FCC atoms, the usual FCC lattice points, are occupied by zinc atoms, and this extra four lattice sites which have been introduced uh, here, in the case of a diamond, it consists of carbon atoms, but in the case of zinc blende structure, they are not of carbon or they are not of zinc, but rather of another atom. So you have the normal FCC, and plus you have these four uh, atoms which are different than the FCC atom. So in this case, the FCC is made by the zinc atom, and these extra four atoms are that of sulfur. So this is called a zinc blende structure, exactly like carbon. The only difference is these extra four atoms are of a different species. Another important material which has a zinc blende-like structure is gallium arsenide, which is a very important material, for example, for optoelectronic devices like solid-state lasers. Let's have have a look at how to describe this diamond crystal. So the diamond crystal, uh, it has an FCC lattice, as I said earlier, but with a basis not consisting of one atom, but rather two atoms of carbon. Carbon placed at 0, 0, 0, and carbon placed at a quarter, a quarter, and a quarter away from the lattice point. So that's the planar view. So uh, you have the FCC lattice points, which are on the faces and on the corners, and apart from them you have uh, an extra atom here, which is represented in the top view by this circle, which is at 1/4 height from the base plane. Then you have an extra atom here near this edge, which is represented by this circle, which is uh, 3 uh, 3/4 above the base plane. And similarly, the two other ones, one occurring here and the other occurring there, represented by these two. The rest is just as you had for an FCC lab. So how to place this basis, two atom bases on the FCC, and to get the final location of atom within the conventional unit cell of diamond. So we start with a reference lattice point, which is at the edge. We place one basis atom of carbon at 0, 0, 0, which means exactly at the lattice point, and the other at 0, 0, 0 plus a quarter, and a quarter, which is this distance away from this lattice point. So you get these two atomic position, which get you this atom and this atom. For the FCC, you need to describe at least uh, four bases to fully describe a conventional unit cell. So that's why you need to have to describe 8 atomic position, because each base consists of 2 atoms, and since you have to describe 4 bases, which means that you have to describe 4 atomic position in this case. So the next lattice point, I consider it a half, and a zero, which is if this is A1, this is A2, so this would be this atom in the lower base plane, which is this one. So you place one atom there exactly at the location, so that would be the 0, 0, 0 atom in the bases, and then you add a quarter, quarter, and a quarter with it, which gives you 3/4, 3/4, and a zero, which gives you this atom. So this location corresponds to this lattice point, which is exactly at the location of the lattice point, and then you place an extra atom at a quarter, quarter, quarter away from this lattice point, and that gives you this another extra atom in the crystal. And similarly you can do the same for the other two lattice sites. There's another important information which I would like to give you about the diamond is that diamond crystal has a tetrahedral symmetry in it. How to see it is if you look at this atom, starting from this atom of carbon, and you go along here, you reach this atom, and then you have three different branches going out of it, or three different um, carbon-carbon bonds going out of this. Uh, so what you have, one carbon atom is connected or is bonded to four other carbon atoms, and this form kind of a tetrahedral like structure. So you have one carbon atom consisted of connected with four other carbon atoms because of this valency of four. So you can look at a diamond crystal as consisting of a combination of arrangement of tetrahedras as well. So this from symmetry point of view, if you want to describe such a circle, it has a tetrahedral like symmetry. Yet another example is that of a sodium chloride crystal. So as you know, sodium chloride is an ionic crystal with sodium chlorine ion. And in the case of sodium chloride crystal, the lattice is an FCC or face-centered cubic lattice, and the bases consist of two atoms, a sodium atom located at 0, 0, 0, and a chlorine atom located at a half, a half, and a half. So you can see the structure here, rather a bit more complicated. But it's easily visualized if you look at just the lower the lower plane or the uppermost plane. It looks something like this. You have four sodium atoms at the corner, one in the middle, and on the edges you have the chlorine atoms. So if you look at the layer in the center, it has chlorine in the middle and on the corners, and sodium at the edges. So just imagine, let's do it for this reference point 0, 0, 0. So if I have just one lattice point here for the FCC, I can add a sodium atom as 0, 0, 0 here, which would be this atom, and the next atom would be and the basis would be a chlorine atom added at a half, a half, and a half, and which would be exactly in the center. Similarly you can do so, because you have four bases in an FCC crystal, so you need to define the atomic position of atoms, and in this case 4 for sodium and 4 for chlorine. You can do the whole exercise here and come up with these atomic positions by adding the lattice points with the bases yourself. So since we are discussing the case of ionic solid, in this case sodium chloride, I would like to also mention here how you derive Madelung constant. If you don't remember the Madelung constant, remember we tried to derive a cohesive energy of an ionic solid uh, such that for the case where Re represent the equilibrium distance between a positive and a negative ion, in the case of a sodium chloride between a sodium atom and a sodium ion and a chlorine ion, and the cohesive energy of a whole crystal is given by such an expression, um, which we used in one of the assignment problems, where Na is the Avogadro number, Re is the equilibrium separation, rho was another distance which you can extract from the bulk modulus, and A was something which we call as a Madelung constant, which depend on the geometric arrangement of ions within the solid or within the crystal. So this Madelung constant is a purely geometrical factor, and we can calculate it for a sodium chloride crystal shown here. So you have sodium ions denoted by small dots, and chlorine ions with larger circles as described here. So Re would be the distance between these neighboring ions, the nearest distance. So the Madelung constant is for an ionic solid is defined in such a way that the Madelung constant is basically a result of a sum of a series of different numbers. The first number in this series would be the number of nearest neighbors. So you start with the sodium atom, and then you find the number of nearest ions. For example, the nearest atom in this case would be this chlorine atom, this chlorine atom, and this chlorine atom, just in this quadrant, and you can imagine that there are other chlorine atom on the other side as well. So you calculate all the nearest neighbor atoms, you put that number in here, and then you divide it by the distance between the sodium atom and its nearest neighbor in the distance of Re, and because Re is already this distance, so in this case this number would be 1. Here you have minus of the sign multiplied by with this factor, and minus, so if so these nearest neighbors are chlorine atoms and chlorine ions, and chlorine ions are negatively charged, so its sign is minus, so minus into minus is a plus, so the first term would be a plus term. Then you look for the second nearest neighbor, and in this case the second nearest neighbor are these sodium atoms which are placed here. For example, this would be one example. Then you find such second nearest neighbors, and then you divide it by the distance between this second nearest neighbor and your original or your reference sodium ion, and then you divide it by 2 in terms of Re, and you divide it, multiply it by the negative of the sign. So because this is a positive ion, so this would be a negative term here, and plus so on and so forth. So the third term would be the third nearest neighbor, and so on and so forth. So this is a diagram which shows the nearest distance. So I've just taken a part of this crystal. So you start with the sodium ion, then these are the two chlorines which are the nearest neighbor, then this is the second nearest neighbor and the third nearest neighbor, and so on and so forth. The distances are given in terms of this Re, where Re is just simple this distance. So for this sodium chloride crystal, you have 6 nearest neighbors divided by the distance in Re between the nearest neighbor, which is 1, and the first term is positive. Second term is you have 12 next nearest neighbors divided by a square root of 2, because the distance between the second nearest neighbor and your reference point is under root 2 multiplied by Re, where Re is basically this distance. Remember, Re is not equal to A. A is the lattice constant from here to here. So just to confirm this. And similarly, you can go on and complete the whole series. And this series converges to a certain number, which is 1.75. And that's 1.75 is basically your Madelung constant. And so basically, this is the geometrical factor which goes into the cohesive energy, which you already used in one of your assignment previously. So in this module, just to summarize what we covered is we started with the concept of bases. How do we define bases, and how can we represent any periodic structure with the help of bases and lattice. More specifically, we were interested in, or we looked at how to represent a physical crystal as a convolution of a Bravais lattice and a basis, such that the basis is made of atoms rather than points. And we looked at a few examples of crystals, physical crystals, which are common or which are widely used in literature.